So this is a reading of characteristics of waves. All waves have the following 4 characteristics. So it's listing things and they're in bold, so they're probably very important, so I'll probably highlight them as well. The amplitude of a wave is the distance a wave oscillates from its resting position. I'm going to highlight that. I'm not sure if I know what oscillate means, and I don't know what resting position means. So I'm going to put question marks over both of these words. I'm going to reread it. The amplitude of a wave is the distance a wave oscillates from its resting position. The larger the amplitude, the more energy carried by the wave. Wavelength. The distance from any point on one wave to a corresponding point on an adjacent wave. These are 2 words, corresponding and adjacent, that I'm also not sure about. Frequency. Frequency is the number of oscillations. So here's that word again. So I need to figure out what oscillations mean. Frequency is the number of oscillations produced in a certain amount of time. The greater the number of oscillations per second, the higher the frequency. The higher the frequency, the more energy carried by the wave. This makes sense to me. The higher the frequency, the more energy carried by a wave, and that seems important. Frequency is measured in hertz. 1 hertz is equal to 1 wave per second. Wave speed is the distance a wave travels in a given amount of time. Waves move faster through some mediums than other mediums. I'm going to have to ask, I wonder what examples there could be of that. Okay, so now here's a good diagram, and it shows me that this is what amplitude is. Amplitude is the wave distance that oscillates. I wonder if oscillate means like moves. I'm going to write the word moves here with a question mark. I wonder if that's what moves, if oscillate means. So there's a picture of what amplitude is. Here is what wavelength is. So wavelength is from one same part of the wave to another same part of the wave. Resting position is just the line that the wave moves along. Oh, here could also be a wavelength. Same spot to same spot. Okay. Kinds of waves. When an oscillation, oh, here it explains it. When the oscillation, the back and forth or up and down movement of a wave is perpendicular. So I know from math that this is what perpendicular means. To the direction in which the wave travels, the wave is called a transverse wave. So if it travels, so a transverse wave is when it's perpendicular to the direction. And then here is an example of a transverse wave. Look at the figure of a transverse wave. The peak or the highest point of a transverse wave is called a crest. So the highest point is known as a crest. And so here's the crest, this high point right here. The valley, or the lowest point, is called a trough. The valley, or the lowest point between 2 crests, is a trough. So this is my trough, and this is the crest. Some examples of a transverse wave include electromagnetic waves and a type of seismic wave, a wave that occurs during earthquakes, called a secondary wave. So here again it shows what perpendicular. So the wave is going up and down to this rest position. Okay, now I have a second type of wave. A longitudinal wave is a wave whose oscillation, and that means movement, the motion. The longitudinal wave is a wave whose movement is parallel. So again, parallel I know from math means like this, to the direction of which the wave travels. So really you're naming the waves and the way that they travel. For example, if you set a spring on your desk and push the end of the spring over and over, you create regions where the coils are close together, called compressions. So close together means compressions, and regions where the coils are far apart, and that's called rarefaction. The compressions and rarefactions move in the same directions in which the wave travels. So I think of like a slinky that's being moved across. I'm going to write like a slinky question mark. Examples of longitudinal waves are sound waves and a type of seismic wave called a primary wave. I think we're just going to be concerned about sound waves. So longitudinal waves are sound waves, and then the transverse waves are the electromagnetic, are light waves. Okay, so I'm going to write that. So transverse are light waves, and longitudinal waves, these are sound waves. I guess I don't see them, but I guess if I could see them, that's how they would look. So here's my compressions, is when they're close together, this part. And this got cut off by the copier, but this must be my rarefaction, where it's spread out. Okay. The other part of the reading has to do with how waves work. As a wave travels, it does work on everything in its path. The wave in a pond do work on the water to make it move up and down. The waves also do work on anything floating on the water surface. For example, boats and ducks bob up and down with waves. The fact that these objects move tells you that the waves are transferring energy. So I think this is the most important part, is that waves transfer energy. Energy transfers through a medium. I don't know what this word, I don't know what they mean by medium. Most waves transfer energy by a vibration of particles in a medium. A medium is a substance through which a wave can travel. A medium can be a solid, liquid, or gas. So that's the most important part. A medium can be a solid, liquid, or gas. It's the substance through which a wave can travel. So if I knock on the door, is the door the medium? That's what I wonder. When a particle vibrates, moves back and forth, that reminds me of the word oscillate. I'm going to write the word oscillate here. I think that means the same thing. As in figure 2, here, moving back and forth, it can pass energy to a particle next to it. The second particle will vibrate like the first particle does. In this way, energy is transmitted through a medium. So it's kind of like if I hit someone next to me and they hit the person next to them, it's transferring the energy along. Sound waves need a medium. Sound waves, those are the longitudinal ones. So I'm going to write that next to here. Longitudinal. Those are those waves. Sound waves need a medium. Sound energy travels by the vibration of particles in liquids, solids, and gases. Sound energy travels by vibration in particles in liquids, solids, and gases. If there are no particles to vibrate, no sound is possible. If you put an alarm clock inside a jar and remove all the air from the jar to create a vacuum, you will not be able to hear the vacuum. A vacuum must be something where there's no air. Other waves that need a medium include ocean waves, which move through water, and waves that are carried on guitar and cello strings when they vibrate. Waves that need a medium are called mechanical waves. Figure 3 shows the effects of a mechanical wave in an Earth's crust, like an earthquake. So one question that I have is, do light waves need mediums?